Alright, so these are additional notes regarding beta oxidation that I would like to just mention very quickly. So, in the beta oxidation process that we have discussed previously, we assume that the fatty acid is completely saturated, meaning no double bonds at all, and that it is composed of even numbers. Because the examples I gave there were 10 carbons, 6 carbons, 4 carbons, 18 carbons, all even numbers. But the question is, well, odd-numbered fatty acids exist. So how would we be able to account for the metabolism of these fatty acids? So the answer is simple. For example, I have let's say, a 17 carbon fatty acid. After one round of beta oxidation, it will become 15. Then it will become 13, then 10, then... what? Math please. 11, then 9, 7, then 5, then 3. And when you reach the 3, you cannot chop this off to get to 1. No, that's not the case. So you stop at 3. You stop at 3. The name of that particular 3-carbon acid here is malonyl-CoA, owing to the 3-carbon malonic acid. So you stop right there. Okay? And what happens is that there is a certain enzyme, I won't mention anymore because it's not part of the curriculum. There is a certain enzyme that will insert a carboxyl group in the middle of the malonyl-CoA. So this becomes a 2-methyl malonyl-CoA. And this one actually has 4 carbons. What happens is that it rearranges to form this. And this is a 4-carbon straight chain dicarboxylic acid, and I hope you have recalled this. Alright? If you remove this and this becomes COOH, it's simply COOH, CH2, CH2, COOH, and that is succinic acid. But with CoA, it's succinyl-CoA. And guess what? Isn't this a metabolite in the tricarboxylic acid cycle? After it becomes succinyl-CoA, you do not anymore chop it off into 2 to get to acetyl coenzyme ACE. No. From this point on, from the time it became malonyl-CoA, it is bound to not anymore undergo beta oxidation, but instead it will go to the tricarboxylic acid cycle. So here, you cannot anymore expect the succinyl-CoA to be split into 2 moles of acetyl coenzyme A. It's programmed that it will go directly to the Krebs cycle instead of beta oxidation. Now, what if we are encountering even-numbered but unsaturated fatty acids? Well, everything will go fine, alright? So, for example, we have a pre-existent double bond here. Remember that in beta oxidation, where is my note? Alright, so in beta oxidation, the first step actually is formation of a double bond. Alright? You dehydrogenate the initial fatty acid. But here, the fatty acyl coenzyme A has this double bond not induced by the first step. So what happens is that it would first allow isomerism or isomerization. Why? Recall that in the natural state, unsaturated fatty acids have their double bonds in the cis configuration. See this? This is of the cis isomerism, right? And in the beta oxidation, the second step, the enzyme for the second step will only recognize this one. And if you look at this, the hydrogen is located here, and then the hydrogen at the other carbon is at the other side. This is of the trans configuration. All right. Enoyl-CoA hydratase, in short, will only recognize the trans-enoyl form, not the cis-enoyl form. So it has to be isomerized in order for it to become trans form, and that is the time that you will go to step number 2. And again, step number 2 is the facilitation of enoyl-CoA hydratase. To add water or to hydrate the enoyl. There it is. You hydrated it with water. So in short, very simple to say that in unsaturated fatty acids, the nutshell of this is you only skip step number 1. And remember that step number 1 produces FADH, right? So meaning that you skip the production of this one. Alright? And that's the only difference for every double bond, So for example, I have 3 double bonds. That means that I will skip production of 3 moles of FADH2. It's that simple because everything else after that is the same as with saturated fatty acids. So that's just a minor difference. In fact, only 1.5 ATP per double bond is lost in unsaturated fatty acids.